Want to solve each and every question based on logic, gates and Boolean algebra? Then watch this video. Because in this, I'll show you how to solve questions related to this topic that have come in the GATE examination. If you're coming for the first time on this channel, do not forget to subscribe. So the first question is, given 1235 in base x is equal to 3033 in base y. X and y is the base radix. We need to find the value of x and y. To do this question, the best way is to convert both the bases, that is x and y, to decimal number system. And we know for doing this, we need to multiply the digits with the positional weightages. So when we do this, we start with the number 1235 in base x and we convert it to decimal. In order to do that, we will start from this side. 5 into x to the power 0 plus 3 into x to the power 1 plus 2 into x to the power 2 plus 1 into x to the power 3. Similarly, for the number 3033, we will again convert it to decimal and we get 3 into y to the power 0 plus 3 into y to the power 1 plus 0 into y to the power 2 is 0, and then we are left with 3 into y to the power 3. So you will get an equation that is x cube plus 2x square plus 3x plus 5 is equal to 3y cube plus 3y plus 3. Now, in order to find out the correct answer among the options given, the best way is that you can just put the values given over here and find out that which value satisfies your equation. In this case, when you will find that x is equal to 8 and y is equal to 6 will satisfy this equation, and hence the answer is A. Let's come to the next question. This question says that we have to convert a number 210 in base 3 to hexadecimal. Again, whenever you want to convert a particular base to any other base, like let's say hexadecimal, so the intermediate stage could be that you can first convert this number to the decimal base, and then from decimal we can convert to hexadecimal. We know that to convert any number to decimal base, we have to multiply it with the positional weightages as per the base of the number system. So for this number, we have 0 into 3 to the power 0 plus 1 into 3 to the power 1 plus 2 into 3 to the power 2. So when you will evaluate this, this is 9 into 2 plus 3. That comes out to be 21. So this number, that is 210 in decimal, would be represented as 21. So the next thing left out is that we need to convert this decimal number to hexadecimal. And to do this, we know that to convert any number from decimal to another base, we need to divide that number with that base. So what we do is we divide 21 with the base for hexadecimal, that is 16. Now we know 16 ones are 16, 21 minus 16 is 5, so you have 5 as the remainder. The answer is written from bottom to top. So hence this conversion is from to hexadecimal is actually 15 in hexadecimal. So your answer to this question is 15 in hexadecimal. Let's come to the next question. So the next question is, we are given that the base or the radix of the number system such that the following equation holds is. For doing such type of question, let us say that the base that satisfies this is equal to x. So now all these numbers like 3, 1, 2, 20 and 13.1 are all in the base that is x for us. So what we'll do is that in order to solve this question and find out the value of x, we will convert each of the number to decimal number system. So we have first 312 in the numerator. So this will become 2 into x to the power 0 plus 1 into x to the power 1 plus 3 into x to the power 2 divided with 0 into x to the power 0 plus 2 into x to the power 1 equal to 13.1. So now we'll start with 3 first. 3 into x to the power 0 plus 1 into x to the power 1. And you know, after the decimal points we have negative powers of the base. So this is plus 1 into x to the power minus 1. Now you just need to solve this equation. So we have in the numerator 3x square plus x plus 2. In the denominator we just have 2x because this is 0 equal to x plus 3 plus 1 by x. So we just need to solve this now. So you can see that we'll have it in this way. 3x square plus x plus 2 divided by 2x is equal to, let's take the the LCM, that is x. So we have x square plus 3x plus 1. X and x gets cancelled. So we have next 3x square plus x plus 2 is 2x square plus 6x plus 2. Now 2 and 2 also gets cancelled with each other. So I am left with x square minus 5x is equal to 0. So this gives me that one of the possible value of x is either x is 0 or it is x equal to 5. So I know that my number system base cannot be 0. So definitely the answer to my question is x equal to 5. So hence the answer is C. So in this way, any question that is based on the number system where you have different bases, you can just reach to the answer by converting them to the decimal number system. Let's move to the next question. Now we have a question related to logic gates. So it is saying us that we have to consider a Boolean function that is z of a, b and c. So this is the diagram given to us for the entire implementation, and we have to choose that among this list which of the following min term will represent the circuit. So in order to do this question, first we should find out an expression for z in terms of this logic gate. So we know that at this point this is the NOT gate, so we are getting b bar. Then b bar is getting AND with c, so at the output of this gate you have b bar c, and then over here you have a plus b bar c. So definitely I have my output z is equal to a plus b bar c. Now I am supposed to find out a min term type of list for my output. Now this list can be obtained when you write the truth table. So let's say I mention the inputs are a, b, c, and my output is z, which is equal to a plus b bar c. So for the 3 inputs we can have 8 possible cases like this. These are all the possible 8 combinations. We can note down the answer for each of this. So when we have this type of thing, this is coming out to be 0. Again, for this case I will have 1 as an output because I have a 0 but b bar becomes 1, and b bar and c will give you 1. So hence the output will be 1 in this case. In this situation I'll have 0, and over here again we will have 0. Now in the last 4 cases you actually don't need to solve the equation because you know that the value of a is equal to 1 in each one of them, and a is coming over here. So in this expression, whenever a is equal to 1, whatever be b bar c, the value of z will always be 1. So I need not solve it, and I can just quickly write down that the answer is going to be 1. Now in order to find the min terms are actually those numbers in the column for which you are getting a 1. So you can see I'm getting a 1 over here, 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 and here. And we know that this is the number that is 0, 1, 2, 3, 4, 5, 6, and 7. So this was my decimal number, and when I converted it to binary, I was getting these equivalents. So hence my min term is actually the summation of all this. So I'm going to write down the corresponding decimal digits wherever I have 1 as the output. That is called the min terms. So hence you have 1, then you have 4, 5, 6, and 7. So my answer is 1, 4, 5, 6 and 7, which is B. Let's come to the next question. Now in this question we have it related to the XOR and the XNOR gates. It says that the symbol this and this represents exclusive OR and exclusive NOR operations respectively. You have to find out that which among these following is not correct. So let us start with the first option, that is A, which is P XOR Q whole bar is equal to P XNOR of Q. Now in this case you really don't need to think much about it, because we know that XOR, if we invert it, then it is going to give you the XNOR. So basically whenever and this expression, you know, this symbol is for exclusive OR. So hence whenever we complement the exclusive OR, we are definitely going to get exclusive NOR. So the first statement is actually correct. So I am looking for incorrect statement, so this is not my answer. Let's move to the next statement. B is P bar XOR with Q should be equal to P XNOR with Q. So we have to check this out. So let's see this. For doing this, we need to first know that any A XOR with B is expanded as A bar B plus AB bar. So if you know this, and in fact you should also know that what is the expression for XNOR. So this is AB plus A bar B bar. If you know these two things, then you can solve the questions based on XOR and XNOR. So let's try it out. We'll just try to evaluate this left hand side according to our expression and see that whether it is equal to the right hand side. So we have the left hand side as P bar. So I'll just consider that my A is actually P bar. So I'm trying to do the complement of A. So when I do in this way, it will become double complement of P. Q plus P bar Q bar. So you are just applying this equation, and you need to just consider that your A is actually equal to P bar. Then I see double complement of P is P itself. So PQ plus P bar Q bar. And yes, this is actually equal to the right hand side, because in the right hand side I simply have P XNOR with Q, which according to my second expression is equal to PQ plus P bar Q bar. So even the second equation is correct. So this is also not my answer. Let's come to the third equation. The third option says P bar XOR with Q bar is equal to P XOR with Q. Now in this case, I need to see that whether this is true or not. Again, I'll put the same evaluation. I'll try to expand A XOR B as A bar B plus AB bar. My A is equal to P bar and B is equal to Q bar. So you will just say this is P bar bar Q bar plus P bar Q double complement. Now this will evaluate to PQ bar plus P bar Q. And yes, this is equal to the right hand side, because right hand side is P XOR Q, which is also equal to the same thing. So even C is not my answer. So in fact, I actually know that my answer is going to be D only, but we need to check it out. So we'll just quickly check that yes, if D is actually the answer. So for the D, or the last statement, I have P XOR with P bar XOR with Q should be equal to P XNOR with P bar XNOR with Q bar. In order to do this, we first need to know that for an XOR gate, whenever A is equal to B, the output is 0, and whenever A is not equal to B, the output is going to be 1. And for the exclusive NOR gate, it is the reverse. So you know that in this case, P and P bar are obviously not equal to each other. So the answer would be 1 for the exclusive OR. And then you have 1 XOR with Q. Again, for the XOR gate, we know that if any one of the input is 0 and let's say the other input is A, your answer will be A itself. It acts like a buffer. And whenever one of the input is 1 and the other input is A, then your output is A bar, the complement. So hence, in this case, we have q bar. Coming up to the exclusive NOR gate, whenever both the inputs are not equal to each other, this will give you 0 as an answer, and 0 XNOR with any element will be equal to the complement of that element. So you will have q bar bar. This will come out to be q. And yes, I got my answer because these two things are not equal to each other, and hence I am pretty sure that my answer is D. Let's come to the next question. Now we have some logic gates given to you. We have to find out that what is the expression for this y. We know that the output of the first NAND gate would be equal to AB whole bar, A dot B bar actually, and then the lower one will be CD whole bar, and this y would be equal to AB whole bar dot with CD whole bar and one more complement, because this is also a NAND gate. Now just to find out that what is y, you need to solve this expression, that is y is equal to AB bar dot CD bar whole bar. Now I apply what I called the De Morgan's theorem, and De Morgan's theorem says that whenever you have A dot B whole bar, this is equal to A bar plus B bar. So applying this theorem over here, I get y is equal to AB bar bar plus CD bar bar. Now double complement of any element is the element itself. So we have AB plus CD. And yes, you have the option D as AB plus CD. So that's my answer. Let's come to the next question. We have a 3-input logic circuit given to us, and again it is a similar type. We have to find out that what is the expression for Z. The Q input that is going to both the gates, and this is a NOT gate, so the output will be Q complement, and from the NAND gate the output will be P dot Q bar whole bar. Then at this side you have QR whole bar, and all these 3 inputs are going to Z, going for Z actually through a NAND gate. So you know the 3 inputs for the NAND gate now, so we can write down that Z would be equal to P dot Q bar whole bar dot with Q dot with QR bar and whole bar. And now just to get to the answer, you have to solve this complete equation. Again, you use the De Morgan's law. So this is very important actually, and it is the same thing, A dot B whole bar. It is true for any number of terms. So over here I actually have 3 terms. So I'll write down the law for the 3 terms, A bar plus B bar plus C bar. This law is true for any n number of terms. So solving this, we'll have Z is equal to, the first term is PQ bar whole complement, the second term is Q, and the third is QR whole bar. So just apply the De Morgan's theorem. This is double complement plus Q bar plus QR whole bar bar. Now we know that the double complement of any element is the element itself, so this becomes PQ bar plus Q bar plus QR. Now we can see that we can have Q bar common over here, so we get P plus 1 plus QR. So this question is now reducing up to a Boolean minimizing type of problem. This is equal to 1 because 1 OR with any element is 1 itself, so this is Q bar 1 plus QR. Now if you notice, then you can apply the distribution theorem. We have the application of the distribution theorem, which says that A plus BC can be written as A plus B dot with A plus C. Let's see then how this theorem is helping us over here. In this case, when we apply, we have Q bar plus Q dot with Q bar plus R. Now this thing reduces to 1 because this is q plus q bar. This is 1 as per the OR gate laws. So you are left out with the answer as q bar plus r. So yes, we have to search for this q bar plus r in the option, and this is the C option, that is q bar plus r is your answer. Let's come to the next question now. Again, we have some combinational circuit and we are supposed to find out the output of this circuit, that is y. So again, we have to find out an expression for y and see that which matches to which of the options given to us. So let's get started. We have the output of this first AND gate is A dot B. Then the output of this is B dot C. And you can see that this A dot B is actually coming over here. So this is a XOR gate. So you have A, B, XOR with BC. Then at this point of time, I am having C coming over here as an input to this gate. So this is A dot B dot C. And finally, I have Y is equal to A, B, C, that is A dot B dot C, XOR with AB, XOR with BC. We can just open up this bracket. So we can start over here and open up this bracket as per the XOR equation. We know that A XOR B is equal to A bar B plus AB bar. So we are just going to apply this. So for us, this is A and let's say this is B. So we'll expand it and we have AB dot with BC bar plus AB bar dot with BC. Now what we can do is that we can just open this bracket. So we have ABC XOR with AB, and as per the De Morgan's law, we have B bar plus C bar plus BC A bar plus B bar. Then if we move further and we open the brackets, we have AB multiplied with this B bar, that is AND with this. So this is coming to be 0. So we will be left with A, B, C bar. And in this side, we'll be left with A bar, B, C. Because the second term will also result to 0 because you have B dot B bar. We can expand it like this. We have A, B, C XOR with A, B, C bar plus A, B, C XOR with A bar, B, C. So you will have 2 XORs now. So now what we can do is that we know we can take common. So let us take AB common from here. We have C XOR with C bar, and at this side we can take BC common. So we'll have A XOR with A bar. Now we know that whenever both the inputs are different, the XOR is going to be 1. So this is AB dot 1 plus BC dot 1. So you have AB plus BC, or we can just say B common. So this is A plus C. So this is the answer. Let's see if we have this B dot A plus C. Yeah, we have B dot A plus C. Let's move to the next question. The next question is, if W, X, Y and Z are Boolean variables, then which among them is incorrect? Wx plus W, X plus Y, this is option A that we are trying to see, plus X, X plus Y. So we'll just open this brackets. We'll have Wx plus Wy plus X dot X is X only plus XY. You can take X common because there are various terms which have X. The first two terms I can just write them once only because A plus A is A only. So this is W plus 1 plus Y plus WY. So this is nothing but X plus WY because all this term reduces to 1. Okay, so hence you have X plus WY and that is only the right hand side. So this option is correct. So it's not my answer because I'm searching for the incorrect option. Let's move to the next question. We have B is equal to Wx bar y plus z bar whole bar plus w bar x, and we have to see whether it is equal to the right side. So we'll first try to open it up using the De Morgan's theorem. This is Wx bar whole bar plus y plus z bar whole bar plus w bar x. Now again we apply De Morgan, we get w bar plus x, and this becomes y bar z plus w bar x. Now you can take w bar common, so we get 1 plus x plus y bar z. So we have w bar plus x plus y bar z. So let's see what is the right side. It is w bar plus x plus y bar z. So even the second equation is not incorrect. Let's go move to the third option now. So we'll see the third option. And yes, we go for the third one. So third one says wx bar y plus xz bar plus w bar x bar whole multiplied with y should be equal to xy bar. So that is what we have to find out. So let us try this. We will just open up the brackets wx bar y, and when we open the second bracket x bar dot x, this becomes 0. So we are left with w bar x bar and then y. So this becomes wx bar y plus w bar x bar y. We can take x bar y common and we'll have w plus w bar. So this comes out to be x bar y. And okay, so just notice that the left hand side and the right hand side are not equal to each other, because over here we have x bar y and this is xy bar. So actually the answer is going to be the third option only. But let us just check whether the fourth is correct or not. So we'll just go to the fourth. W plus y, and then you have wxy plus wyz. So we'll just open this bracket, multiply each one of them with these terms. We'll get this, and then wxy plus wyz. Now you can see these are two terms written two times. Wxy also two times and wyz also two times. So this means that a plus a is actually a only. So this is equivalent to wxy plus wyz. And that is my right hand side. So yes, I know that my third option is actually a correct statement, the fourth one. So yes, my answer is going to be C. Let's move to the next question. Now we have, consider the following Boolean expression for f. F is PQ plus P bar QR plus P bar Q R bar S. So we have to just try to minimize this. So let's see if there is anything that is common. So you can see P bar Q is common in the first two, the second and the third term. So we can take this common and we have P bar Q common. So we'll say R plus R bar S. Now you can apply the distribution theorem over here. PQ plus P bar Q, R plus R bar, and then R plus S. So this becomes PQ plus P bar Q, R plus R bar is 1. So we are left with R plus S. We open this bracket, we get PQ plus P bar Q R plus P bar Q S. Now what we can do is that we can take Q common from, let's say, the first term and the second term. So let's try that out. So when we take Q common, we get P plus P bar R plus P bar QS. Again we apply the distribution theorem, so you will get over here P plus R actually, because one term will be p plus p bar, which will be 1. So we have this, and hence we get pq plus qr plus p bar qs. Again, we can do the same procedure in the first and the third term. So again we do this, we'll get q common. So we have p plus p bar s plus qr. So again you will have q dot with p plus s plus qr. And finally we have pq plus qs plus qr. This is your answer. So yes, pq plus qs plus qr. So answer is actually A. Let's move to the next question. In this question we have again some circuit with the logic gates. So we have to find out the output, that is F. So we know that this first gate is an XOR gate. So this is X XOR with Y. This is the XNOR gate. So this is actually X XOR Y, because this output is coming from here to the input of this gate. So this thing XNOR, because this gate is exclusive NOR gate, this gate is an exclusive NOR gate, and hence we have Z, and now F is equal to X XOR with Y and with X XOR with Y XNOR with Z. So this is what is F, and we have to find out the reduced expression for this. So what we can do is we can just we can just open up the bracket. So we have X XOR Y dot with X XOR Y and XNOR with X XOR Y dot Z. So you have A dot A is A only. So this is X XNOR with Y, XNOR with X XOR Y dot Z. We can take X XOR Y common, and we have 1 XNOR with Z. Now XNOR gate, if one of the input is 1, it behaves like a buffer actually. So this is equal to X XOR with Y, and this thing evaluates to Z as per the exclusive NOR gate. So hence we have, just open this bracket, you have X Y bar plus X bar Y. This is how XOR gate is expanded. Dot with Z. So when we open the bracket, we have X Y bar Z plus X bar Y Z. And yes, it matches up to which equation? I think the first one, X bar Y Z plus X Y bar Z. So yes, your answer is A. Let's move to the next question now. Again, we have a circuit given to us, and it says that if C is equal to 0, the expression for Y is. This 0 is traveling to the input of the NOT gate. So this will definitely be 1 always. So this is fixed. And also this 0 is coming over here as an input. But this is a OR gate. So we cannot say that if any one input of a OR gate is 0, we cannot predict the other the answer without knowing the next input. So in this case, we need to know that the output of this would be actually the second input which is coming over here. And this input is A plus B whole bar. So at the output of this OR gate, we'll be getting this, because A plus B whole bar will come over here first, and because C is equal to 0, the output of this OR gate will be A plus B whole bar. Then this A plus B whole bar is getting as an input to another OR gate, the second input to which is A dot B, because we have a AND gate previously. So the output at this point will be A plus B whole bar plus with AB, and this all is going to your output, that is y. So finally we can say that y is equal to 1 dot a plus b whole bar plus ab and whole bar of this. So this is going to be y is equal to, you have this as a bar b bar plus ab whole bar. Now this thing, if you notice, the bracket inside is actually a x nor with b, and we have a whole complement here. So this means that y is actually the complement of an XNOR gate, which is equal to a XOR with v, which is a b bar plus a bar b. Hence the answer is the option that is a b bar plus a bar b. So this complete network is actually for an XOR gate. So let's come to the next question. We have over here, now this is something different. It is asking you that the output of y in the circuit would always be 1 when. So at what situation the output of y would be always 1. To find out this, let us first see that what is the output y in terms of p, q and r. So if we do over here, this is p and q. So this will be pq whole bar. This will be qr whole bar. And this will be pr whole bar. Now this becomes pq bar dot qr bar whole bar, and again it is passed through a NAND gate. So you will just have the complement removed from here because it will become double complement, so it will become the element itself, and hence we can say that y is equal to pr bar dot with pq bar qr bar whole bar. Now we just need to solve this out. So when we open it as per the De Morgan's law, we have y is equal to PR double complement plus PQ bar dot QR bar whole bar. Again we apply the De Morgan. This is double complement, so it's the element itself. Over here you will get PQ double complement plus QR double complement. This is PR plus PQ plus QR. Now what does this expression tell us about the answer? So this is what is y equal to. So you have to find out that when will y be equal to 1. So it is saying that when 2 or more of the inputs p, q and r are 0. Now if any 2 inputs are 0, I know that each of these terms will reduce to 0 only. And hence this is not the correct answer. The second option says that when 2 or more inputs p, q, r are 1. Okay. If any 2 inputs are 1, then, or let's say all the 3 are 1, then I'm going to get definitely one of these terms to be equal to 1. And if any one of these terms is equal to 1, then my search is finished, and yes, my output will be always 1. So definitely the answer to this question is B. Let's come to the next question now. Which of the following circuits is not equivalent to a 2-input exclusive NOR gate? Now you can see this is again the similar question that we have been dealing till now. So if you just see, this is actually, if I look at the first option, it is first I have an XOR gate and then I do an inversion of this. So this is obviously an XNOR gate as a result. So this is not my answer. If I look at the second question, the second option, then this is X bar, then this is X, Y. So this will be X bar, Y bar. And then we have X bar exclusive XOR with Y bar. Now this comes out to be, actually we have done it in the previous question also. This comes out to be X XOR with Y only. And when you do the NOT operation for this, it will come out to be X XOR with Y. So even second is not the answer. Let's move to the third option. You have X over here. So this will become X complement. This is, let's say, Y. And we have already seen that X bar XOR with Y is equal to X XOR with Y. So even this is correct. Now let's come to the last one, that is the fourth option. Over here we have let's say this is x and this is y. So this is x y bar and this is going to be y bar plus x. Then we have over here x y bar whole bar because this is a NOT gate. So let's say the output for this will be x whole bar x y bar dot with y bar plus x whole bar. So we'll open it as per the De Morgan's law. You have x y bar double complement plus y bar plus x complement. Now this becomes x y bar plus y dot x bar. This is coming out to be an XOR gate and it is not an exclusive NOR gate. So your answer is D. So the D network does not equivalent to a exclusive NOR gate. Let's come to the next question now. We have to simplify a sum of product terms which is given to us. We have P plus Q bar plus R bar, P plus Q bar plus R, P plus Q plus R bar. Now what you can do is you can see that you can take common P plus Q bar from these two things, and this is actually called the transposition theorem. So we have transposition theorem which states that if you have A plus B and A plus C, this is equal to A plus BC. So applying this theorem, we have P plus Q bar plus R bar, and over here you are left with P plus Q plus R bar. Now this R bar is equal to 0, so we have P plus Q bar and then P plus Q plus R bar. Again we can take P common and apply the transposition theorem again. So this is P plus Q bar dot with Q plus R bar. So we have P plus, we expand this bracket, this is Q bar dot Q plus Q bar R bar. This comes out to be 0, so we have P plus Q bar R bar. So your answer is P plus Q bar R bar, which is B. If you like this video, hit the like button below, share it with your friends and be sure to subscribe. I will see you in the next video.